The purpose of this lab, Oscillations, was to track a spring mass system where the only forces we are measuring are spring force and gravitational force. In the video, an object attached to a spring moves in both the x and y direction, therefore creating an oscillation motion. With the system chosen, the energy principle is demonstrated since there is zero work done on the system and the total change in energy is zero. I analyzed the provided video using Tracker to collect the object's position data over time. To ensure the data was accurate, I used a calibration stick to establish the initial relaxed length of the spring with the mass attached, which was 0.7 meters. I then set the coordinate system to have the origin at the point of attachment of the spring, with the y-axis running along the spring in the negative y direction. When the video is run, Tracker collects a series of XY data points, producing a position versus time graph that demonstrates oscillatory motion. When creating a computational model for this motion, I used Newton's second law and the energy principle to create an accurate model. To update the object's velocity and position, I used two variations of the formula. First, final velocity was equal to initial velocity plus the net force over the object's mass times delta t. Second, the object's final position was found by taking its initial position and adding the final velocity times delta t. These were both updated at each iteration of the while loop in my code. Next, to calculate the changes in energy, I used the formulas shown here. The total change in energy was equal to the sum of the individual changes in kinetic energy, gravitational potential energy, and spring potential energy. There were a few values I had to calculate for my observed model to use in my code. First, to find t, the average period of oscillation, I found how much time on average it took for the object to complete a single rotation. I found this to be 1.6507 seconds. Next, I calculated the spring constant using the formula k is equal to 4 pi squared times the mass of the object over the average period squared. After plugging in the mass of the object 0.402 kilograms and the t found previously, I found that the spring constant was equal to 5.8244 newtons per meter. Lastly, I needed to find the relaxed length of the spring by using its initial length of 0.7 meters and subtracting the mass of the object times the gravitational constant divided by its spring constant. I found this value to be 0.0236 meters. Now, with all the necessary initial values found, I could create my code. Beginning with the starter code, I entered the object's mass, initial position and velocity, the spring constant, and relaxed length from my observed model. I also added the length of the spring to be the object's position minus the spring's position. L had to be this vector divided by its magnitude, and the total stretch to be L minus L naught. Using the equations mentioned earlier from the energy principle, I calculated each of the individual forces and total force acting on the system. Within the calculation loop, I set these initial energies and set the net force equal to the sum of spring force and gravitational force. The gravitational force was equal to the negative of the gravitational constant times the mass of the object, and the spring force was equal to the negative spring constant times its stretch times L hat. I also included the variations of Newton's second law to update the object's position and velocity. To update the spring, the same formulas as before were used. Lastly, the change in energies were set to be the current energy minus the initial energies established before the calculation loop. When the program is run, I upload a CSV file of my observed model so that its position data can be compared to that of the computational model. 3 different visuals are produced, the first showing the actual motion of the two models. The second is a graph of the change in energies where the total change in energy is 0 since there is 0 work done on the system. Lastly, a graph comparing the position data of the two models is shown, which clearly tells that the computer model overestimates the motion of the ball. This is because in the computer model, drag force is not taken into account. Drag force is a resistance force that acts on the direction opposite of the object's motion. Therefore, without this factor in the model, it will predict the motion to move at a faster pace in both the x and y direction. There should be a total energy change of 0 to satisfy the energy principle since there is 0 work done on the spring mass system. However, the graph shows the total change in energy is nearly, not exactly 0, simply due to a slight inaccuracy errors in the code. The variation is extremely small, however, so since it is approximately 0, the energy principle is satisfied. When calculating the average period, when using the x direction, as I did in my computational model, it was found to be 1.6507 seconds. However, when using the y position to calculate the average period, I found t to equal 1.492 seconds, meaning the two differed by 0.1587 seconds. The two values differ as the x period of oscillation is defined as the spring's movement from left to right, while the y period is defined by the upward-downward motion of the spring. The x motion depends on gravity, while the y motion depends on the stiffness of the spring. Since the two motions are affected by different factors, their periods will not be exactly the same.